Hello members of Management Science 394, Section J11. Our group decided to do project option number 3, Gamecocks drone service. Before jumping into our project option, we wanted to introduce to you the members of Another Day, Another Data. Going from left to right, we have Ethan Noble, Josephine Bayer, Kaylee Wheeler, Tyler Guglielmo, and Xavier Scribner. Just a little intro to our group project option. Gamecocks Drone Service Incorporated, also known as GDS, is a package delivery service company using drones. GDS is part of the Columbia metropolitan area and currently delivers about 1,250 small packages a day to 1,250 customers in 10 different cities using 10 different drones. This makes roughly 125 drops for one city. Our team was responsible for making a more efficient route for one city drone. To start working on the solution, as a group, we organized all the data and calculated each distance for the drop location in relation back to the destination that it came from, which started at 00 and ended at 00, also known as headquarters. The equation used in this process is the distance formula shown in the top left corner. Below this formula, you can see the first 20 drop sequence IDs that we performed the distance formula on. From there, we created a scatter plot with straight lines and markers that demonstrated the initial route without any modifications to it. You can see this on the right. We then needed to find a way to make a more efficient drop route. We started by zoning and grouping the data within certain parameters. The first action taken for this strategy was to create a threshold from the 00 point all the way to the 99.99, which would split the graph in half and give a guideline as to what points to follow and, in a sense, show us what destinations to choose next, leading all the way to the farthest points. You can see this sectioned off as the red line drawn on the graph. By visually looking at the graph, the original route crosses over this line many times, causing lots of backtracking and extra traveling that can be eliminated. Next, after splitting the graph in half, we went even farther into zoning the graph by grouping drops every 25-25 areas. We dissected each area to figure out the best route for each specific zone on the top half of the graph. At this point, we were aiming for anywhere around 500 miles once we reached the halfway point near the 99.99 area, and that's exactly what we got. On the left, you can see the top of the graph from the headquarters to our furthest point. On the right, you can see our last coordinates leading up to the halfway mark and our halfway mileage of 535.89 miles. After reaching this point, we essentially did the same strategy on the lower half of the graph and started to zone parts of the graph with the most efficient route back to headquarters at 00. After grouping the lower half of the destination points, we continued the route and tried to limit the number of crosses we had to keep the lowest mileage possible. We then put these two graphs together to create a single route and a single line. In the top left corner, you can see the initial route, and in the bottom right corner, you can see our group's new efficient drop-off route. Looking at these two models next to each other, you can see that our new model does not jump over the red line, but rather goes in almost a complete circle without backtracking. By doing this, we reduced the mileage significantly from the start point of 2,999.06 miles. When we finished the route back at headquarters at the 00 point, we finished with a total mileage of 861.25 miles and successfully completed an efficient route below the 1,000 mileage maximum.